Welcome to AI Paper Slop, where we cut through the noise and just get straight to the architecture. Today, you and I are unpacking a paper that completely rethinks how we handle context and working memory in LLMs.
It really is a fundamental shift in how we approach the token bottleneck.
Yeah, absolutely. So the paper is called T2MLR Transformer with Temporal Middle Layer Recurrence by Ziyang Cai, Xingyu Zhu, and the research team over at Princeton. Let me just give you the core insights right up front.
Always the best way to start.
Right. So standard transformers suffer from this massive information bottleneck during autoregressive decoding. Every single time they generate a token, they are basically forced to compress these rich, high-dimensional latent reasoning estates back into a super sparse token space.
Which is incredibly inefficient for any kind of complex reasoning.
Exactly. So T2MLR solves this by routing a cache representation from a deep middle layer of the previous token directly into a shallower middle layer of the current token.
And it does this with surprisingly little overhead.
Literally under 8% inference overhead. It boosts multi-hop and math reasoning significantly, and this is the absolute kicker for you ML engineers out there. You do not even have to pre-train this from scratch.
Right. You can just retrofit it directly onto existing pre-trained models.
Yeah, it's wild.
Right.
So to see why a structural shift of this magnitude is even necessary, you really have to visualize what happens over the hood of a vanilla transformer when it attempts, multi-step reasoning.
We all know the bottleneck exists, but looking at the why reveals this fundamental flaw in how the models process information.
Right, because when you feed a transformer a prompt, it doesn't process that text as just this homogeneous block of compute. We know from mechanistic interpretability specifically, the probing work from Tenney, Jeva, and Meng, that there's a strict division of labor across the layers.
Yeah, open up any standard large language model, and that stratification is just obvious. The earliest layers function almost exclusively as lexical and syntactic parsers.
Basically just mapping out the grammar.
Exactly. Identifying parts of speech, building the raw structural scaffolding of your prompt. But as the data propagates deeper into the middle layers, the computation becomes highly abstract.
That's where the actual thinking happens, right?
Right. That middle section is the locus of actual reasoning. It handles entity resolution, logical deductions, the complex internal mathematics of whatever you queried.
Okay, so what do the late layers do then?
The late layers just serve as a projection mechanism. They detangle that highly abstract representation back into the vocabulary space so the model can actually predict the next discrete word.
Which brings us right to the actual bottleneck. Let's say you ask the model to generate a complex mathematical proof. The model builds up this beautifully complex, high-dimensional reasoning state in those middle layers. It really understands the underlying logic.
It has the whole concept mapped out in its latent space.
Right. But then standard autoregressive decoding forces it to spit out a single token, maybe just a comma or, the number 42. And in doing so, that entire rich internal state is just wiped out.
Completely erased.
Yeah. For the next token, the forward pass has to start all over again from a heavily compressed embedding of that one new token.
Yeah.
It's like, well, imagine having a brilliant mathematician who is locked in a room and they're forced to communicate their entire complex internal thought process using only single-word flashcards before they can move to the next step of an equation.
That is a perfect analogy. They write the number 42 on a flashcard, slide it under the door to themselves in the next room, and then
they just stare at it.
Right. They stare at that 42, having completely forgotten the 3 pages of calculus they just did to arrive at that number in the first place.
That's so inefficient.
It really is. To continue the proof, the mathematician, or the attention mechanism in this case, has to look at the entire history of flashcards generated so far and somehow reverse engineer the intermediate logic from scratch.
That whole unembed, decode, embed cycle is just fundamentally broken for tasks that require a persistent, evolving latent state.
Completely broken.
So if you're listening to this and wondering why we haven't just fixed the flashcard problem already, it's not for a lack of trying. Other architectures have attempted to solve this.
Oh, absolutely. By looping the entire network multiple times or feeding latent states back into the input embedding.
But there are massive trade-offs there. If you loop a 100-layer network 3 times for every single token, you're inference compute budget absolutely skyrockets.
It becomes undeployable.
Right. And if you force the latent state back into the input embedding, you are basically forcing advanced abstract reasoning to live in a shallow embedding space.
A space that was only ever designed to handle basic vocabulary mapping. It just doesn't fit mathematically.
Exactly. So T2MLR creates a structural bypass to fix this. The Princeton team designed what they call a constant size recurrent cache, which they denote as R sub T.
And this cache maintains the exact same dimension, D, as the standard hidden state of the network.
Right. So during the forward pass, the architecture intercepts the output from a deeper layer. Let's call it layer end at time step T-1.
Instead of letting that abstract information die at the output projection, it pipes that high-dimensional data directly into an earlier layer start at the current time step T.
So that temporal shortcut grabs the abstract reasoning state before it gets projected out into the vocabulary and pipes it directly into the next token's reasoning phase.
It's a continuous bridge for the model's working memory.
But wait, mathematically, if I'm looking at the vector space, you can't just smash two high-dimensional vectors together. There has to be some sort of traffic controller determining how much past context to actually let in.
Oh, definitely. You'd ruin the current representation otherwise.
Yeah, because if you're directly injecting deep, highly abstract representation from a previous token into the processing stream of a new token, I would expect catastrophic interference. How does the model avoid latent hallucination?
Or it just starts seeing ghosts of previous tokens.
Exactly, where it completely loses track of the actual current input.
Yeah.
Do they just use a standard attention gate to manage this?
Actually, no. A standard attention gate would be way too computationally heavy, and it could seriously disrupt the primary residual stream. Instead, they deploy a learnable representation fusion module, denoted as phi.
Okay, how did phi work?
It uses input-independent learnable scalar gates, specifically gamma-cur for the current token's representation and gamma-rec for the recurrent cache. They couple these scalar gates with element-wise sigmoid functions.
Right, and a sigmoid function basically squashes any value between 0 and 1, so it acts like a highly precise, literal valve for the data stream.
Precisely. But the true brilliance of this setup lies in the initialization. The researchers initialize both of these scalar gates entirely at 0.
Oh, wait. If they start at 0, then at step 0 of training, the entire recurrent pathway is effectively turned off.
Exactly. The model doesn't even know it has a bypass. It's just a vanilla transformer at that point.
Wow, that's clever.
The network begins its life relying purely on its standard attention mechanisms. But as training progresses and it encounters complex reasoning tasks, the gradients start shifting those gates.
So the model learns when to open the valve.
Right. The gamma-cur gate actually converges to a negative value. Because of the sigmoid function, this systematically suppresses redundant information coming from the main residual stream.
And what about the recurrent gate?
Concurrently, the gamma-rec gate converges to a positive value, actively pulling in the recurrent state.
So it smoothly learns to leverage the recurrent cache as an additive refinement. It's only pulling from that temporal memory when that past abstract state actually provides a mathematical advantage over what the current token offers.
Exactly. It inherently protects the primary residual stream from the feature collapse or hallucination you were worried about.
That is incredibly elegant. The transition from a standard transformer to a recurrent hybrid happens totally organically, without blowing up the latent space.
The network basically dictates its own reliance on the recurrent memory based purely on the loss gradient.
Okay, the theory is undeniably elegant. But, in this field, elegant mathematical theories don't always survive contact with the compiler. We've seen so many neat tricks fail to actually move the needle in practice.
Oh, all the time.
Right. So how do we know this specific wiring provides a tangible advantage over just, say, using an RNN for state tracking or a standard transformer for context?
Well, the Princeton team designed a highly specific, brutal synthetic test called the S5 Retrieval Benchmark just to isolate these capabilities.
S5 retrieval. What does that actually test?
The task forces the model to perform two conflicting operations simultaneously. First, it has to track permutation group compositions, which is essentially a complex, continuously updating mathematical state.
Okay.
Second, it must simultaneously perform in-context dictionary retrieval based on that evolving state.
So if you're trying to visualize what tracking permutation group compositions actually means, imagine trying to mentally track the exact positions of every single card in a deck while someone continuously and rapidly shuffles them.
That's a great way to picture it.
And then on top of that, occasionally they ask you to pull a specific definition out of a dictionary based on the suit of the card at position 14.
Right, it's a massive cognitive load. Now, an RNN, like a 4-layer LSTM, inherently understands how to track sequential state changes. It's built for the shuffling part.
But it fails the S5 retrieval benchmark completely, right?
Completely. Because it bottlenecks all its retrieval operations into a fixed dimensional state. It simply lacks the bandwidth to act as a massive lookup table for the dictionary retrieval part of the task.
And a standard transformer fails for the exact opposite reason.
Exactly. It excels at in-context retrieval because self-attention can look across the entire context window simultaneously, but it lacks recurrent memory, so it fails at tracking the persistent shuffling of your hypothetical deck of cards over long sequences.
Because the self-attention mechanism is forced to reconstruct the entire history of the shuffles from scratch at every single layer.
Right. And as the sequence grows, the required depth of the network scales logarithmically. Eventually, the transformer hits a wall where exact match accuracy just flatlines at absolute zero.
Yet T2MLR, when matched parameter for parameter against these baselines, achieves near-perfect sequence exact match accuracy up to 32 states.
While the standard architecture's flatline, T2MLR basically aces the test.
It's amazing. The recurrent pathway is acting like a continuous short-term working memory to track the card shuffles, while the standard transformer attention backbone preserves that massive reference library of the context window for the dictionary retrieval.
The inductive bias works exactly as theorized. Passing a synthetic torture test like this proves the underlying theory is sound. It demonstrates the architecture genuinely captures the strengths of both paradigms without succumbing to their weaknesses.
Yeah, but synthetic benchmarks are notoriously easy to overfit. We really need to see how this architecture handles the messy, ambiguous reality of natural language and complex math reasoning.
Beating toy data is one thing, performing in the wild is another, entirely.
Exactly. So how did they test that reality?
They grafted T2MLR onto the small LM backbone. They scaled the architecture across 135 million, 361 million, and up to 1 billion parameter variants.
That's a solid range to prove scaling.
Yeah, and they pushed these models through a highly respectable pre-training run on the FineWeb IDU dataset, exposing them to up to 50 billion tokens.
Okay, and the downstream results.
Following pre-training, they evaluated the models on a suite of rigorous reasoning tasks. GSM-OG for mathematical reasoning, PROS-QA hard for logical graphs, Hotpot QA for multi-hop natural language questions, and complex variable assignment tasks.
And how did it do against the baseline?
The T2MLR models consistently outperformed the data and parameter-matched vanilla transformers across every single benchmark.
The performance bump is super impressive. But there's a detail hidden in these results that I find completely fascinating, and it revolves around what layers they actually connected.
The 20% finding.
Yes. If I were designing this, my instinct would be to give the model as much continuous thinking time as possible. I would take the output from the final reasoning layer, say layer 30, and loop it all the way back to layer 1. Just maximize the runway for continuous thought.
It seems intuitive, right?
Yeah, but the researchers found that full layer recurrence actually degrades performance compared to localized middle layer recurrence. The optimal setup, the one with the highest average scores across all these benchmarks, came from looping just layers 13 to 18.
Which is only 20% of the network.
Right. Why on earth does shrinking the recurrent loop to just a fraction of the layers produce a smarter model?
Well, the answer lies in that mechanistic analysis of the transformer layers we discussed earlier. Recall that the earliest layers are dedicated entirely to raw syntactic parsing, and the middle layers handle the abstract reasoning.
Okay, I'm following.
If you take a highly refined abstract mathematical state from layer 30 and blindly force it back down to layer 1, you introduce catastrophic noise into the system. You're forcing the network to remix deep abstract logic with low-level grammatical processing all over again.
Oh, I see the friction there. You're essentially asking the part of the brain that identifies basic nouns and verbs to somehow process advanced calculus.
Exactly. It dilutes the reasoning state because the early layers aren't equipped with the weights to handle that level of abstraction.
So the 20% sweet spot layers, 13 to 18, acts as a surgical strike. By restricting the recurrent loop exclusively to the middle layers, the architecture lets the early layers execute their syntax mapping completely uninterrupted.
And it allows the late layers to handle vocabulary projection uninterrupted, too. The recurrence only loops the actual thinking part of the brain.
It mathematically proves that recurrence is most powerful when it operates strictly at the correct level of abstraction.
That is so cool.
It really is a profound insight into architecture design. But wait, this localized 20% loop sounds incredibly efficient in theory. But by introducing a recurrent dependency between tokens, haven't we just broken the very sequence parallelism that makes transformers trainable in the first place?
You've hit on the major technical hurdle.
Right. If token T's middle layers physically require the output of token T-1's middle layers, you can't process the whole sequence at once. Standard transformers are fast to train because they calculate everything in parallel. How does the compiler not just choke on this sequential dependency?
The compiler absolutely would choke if you tried to unroll that dependency sequentially during pre-training. The process would grind to a complete halt.
How that way it solve it?
The researchers implemented an approximate temporal parallel scheme utilizing Jacobi fixed-point iterations.
Okay, unpack that for me.
Instead of waiting for token T-1 to completely finish its processing, the system performs a standard independent forward pass for all tokens simultaneously to generate a baseline guess.
Ah, so it guesses first.
Right. Then it runs iterative refinement passes, specifically 16 passes, meaning D forward equals 16, running just through that localized middle recurrent block. This allows the hidden states to iteratively converge toward the true recurrent state while maintaining parallel computation across the GPUs.
I imagine that bridging sequential logic with parallel approximation isn't cheap, though. You're doing 16 refinement passes just to estimate what an RNN would do naturally. What does that actually do to the training budget?
It imposes a significant tax on the compute budget, no question. Depending on the exact size of the recurrent block you're training, those Jacobi iterations make training roughly 2 to 4 times slower in wall clock time compared to a vanilla transformer.
Wow, that is a brutal hit, especially since pre-training is already the most capital-intensive part of the AI pipeline. You're essentially quartering your training speed.
You are. But the trade-off, and this is where the architecture really proves its worth, is what happens at inference time.
Right, because if you look at other methods for extending thinking time, like looped transformers or injecting pause tokens, they just multiply your inference compute.
Exactly. If you loop a network 3 times to think longer, your inference is 3 times as slow and 3 times as expensive.
But with T2MLR, you aren't doing 16 Jacobi iterations during inference.
Not at all. At inference time, generation is strictly sequential anyway. You are only generating 1 token at a time. Therefore, you simply pass the cache from the previous token directly into the next token's middle layers.
It's just a single forward pass.
A single forward pass with just a minuscule fraction of extra matrix multiplication at the fusion gate. The inference overhead is a maximum of 8% per token.
So the architecture trades a massive upfront training cost for a permanent, highly efficient inference upgrade.
Exactly.
And this brings us to what I think is easily the most exciting part of this entire paper. You don't even necessarily have to pay that massive upfront pre-training tax at all. The retrofitting experiment completely blew my mind.
For practical adoption in the industry, the retrofitting experiment is absolutely the most critical finding in the paper.
Tell them what they did.
The team took a standard, fully baked small m2 1.7b instruct model right off the shelf. They physically grafted the recurrent fusion pathway into its middle layers.
And instead of initiating a massive pre-training run from scratch to teach the model how to use this new pathway,
they simply fine-tuned it for one single epoch on the open math reasoning dataset.
Wait, they just took a pre-trained model, surgically inserted the bypass into the weights, and ran a brief fine-tuning run. They didn't have to restart the whole training process?
That's exactly what they did.
What were the benchmark numbers on that? I mean, that sounds too good to be true.
The results were staggering. A standard version of the 1.7 billion parameter model, fine-tuned identically on the same data but without the recurrent graft, hit a score of 35.78 on GSM-8K.
Okay, standard baseline.
The retrofitted T2 MLR model jumped to 39.88.
Wow.
And on the much more rigorous Math 500 benchmark, the baseline model achieved a 12.8. The retrofitted model surged to 18.00.
That is wild. For you listening, think about the real-world analogy here. It is exactly like taking an off-the-shelf gas engine and just bolting on a hybrid electric motor.
That's a great way to frame it.
You don't have to redesign the chassis. You don't have to build a new factory. You just add the module, run a quick calibration, and you instantly get a 40% boost in horsepower.
For the ML engineers trying to deploy smarter models on tight budgets, this lowers the barrier to entry to almost zero.
You don't need a massive GPU cluster to pre-train a recurrent model from scratch.
Yeah.
You can just surgically upgrade the weights you already have.
It entirely redefines the life cycle of a deployed model. If architectural upgrades can be grafted onto existing latent spaces with minimal fine-tuning, the capital expenditure required to stay at the cutting edge drops dramatically.
It's huge.
Yeah.
Let's distill what this means for the broader field of AI architectures.
Yeah.
T2MLR proves that breaking the token bottleneck doesn't require abandoning the transformer architecture for a pure state space model or an RNN. And it certainly doesn't require forcing your model to do massive computationally heavy loops over its entire depth. It just requires a carefully gated surgical bypass in the middle layers, preserving the working memory exactly where the abstract reasoning actually lives.
It forces a fundamental reevaluation of how we view depth and memory in neural networks. We are learning that the precise location of the memory mechanism within the network stratification is just as critical as a memory mechanism itself.
Absolutely. And that leaves you with a really provocative thought to chew on today. The retrofitting success on a 1.7 billion parameter model is a massive signal for the industry.
A huge signal.
If we can successfully retrofit a small model to simulate deeper, continuous thought with just a single epoch of fine-tuning, what happens if we applied this exact middle layer graph to open-weight giants like Llama 3 or Mistral?
The potential upside is astronomical.
Could the future of open-source AI be less about spending millions pre-training ever larger models from scratch and more about architecturally upgrading the latent spaces of the models we already have sitting on our hard drives?
We might not need to reinvent the wheel every time.
Maybe we don't need to give the models bigger flashcards. We just need to give them the architecture to keep their train of thought. Thank you for joining this session of AI Paperslop.